And then number 5, just like addition and subtraction, number 5, you can split the limit over multiplication. So this says the limit of f of x times g of x is the same as the limit of f of x times the limit of g of x. So another example, I just say as x approaches c, and let's have, well, how about we do this? X plus 1 times x plus 2. This means I can split it into the limit as x approaches c of x plus 1 plus, not plus, times the limit as x approaches c of x plus 2. So all I did was take 2 terms. It's multiple terms. It doesn't have to be 2. However many terms you have is how many limits you can split it up to. So I'm just keeping it simple by writing 2 terms there. I had 2 terms connected by multiplication, and now I have 2 limits connected by multiplication. Okay. And then number 6 says the limit can be applied over division. So if you can apply it over multiplication, you can apply it over division. So number 6 says the limit as x approaches c of, let's just say, x over 2. I can split this into the limit as x approaches c of x over the limit as x approaches c of 2. That's it. I can apply the limit to the numerator. I can apply the limit to the denominator. And then let me see if I can move these up. Let's see. Move it there. There we go. Okay. And then 7 says the limit can be applied into any type of radical. So it says the limit of the nth root of f of x can be made into the nth root of that limit. So you take that limit and apply it into that radical. So number 7, if I said the limit as x approach some number c of the cube root of x plus 1, I can just rewrite this as the cube root of the limit as x approaches c of x plus 1. That's all. These are your algebraic limit properties. They show you how you can manipulate limits if you need to. Any questions on those?
No, I'm just copying 7.
We good?
It's kind of like logs a little bit.
Yeah. It's almost exactly like logs, right? What you can do with them. Nothing but algebraic properties. Okay. The next limit property is called the direct substitution property again. So limits of polynomial and rational functions. So all number 1 says is if you have the limit as x approaches f of x, as x approaches c, then all this says is, hey, plug in c and simplify your polynomial. So it's part of the direct substitution. It just says plug that number in and simplify. Nothing crazy. 2 is the limit for a rational function. So again, all this says is plug in that number c and simplify, but make sure it whenever you simplify, because remember, a rational function is a fraction. So if you plug the number in and you get 0 in your denominator, well, we're going to have to go back and fix it. But all this property says is, hey, sometimes it's easy enough just to plug in the actual limit. That's all you have to do, which we are going to apply down below. All right. So using the limit properties, evaluate the limit. Okay. Well, guess what? Using that polynomial property above, what number are you going to plug in for x?
3.
That's it. So if we took a peek at this, I'll rewrite it. we're going to say the limit as x approaches 3 of x squared minus 4x. By that polynomial property above, all this says is, hey, plug in 3 and simplify. So you're going to get 3 squared minus 4 times 3, which will give us 9 minus 12. And our limit is going to be what?
-3.
That's it. Aren't limits easy?
Yeah, but I think they're gonna get harder.
They look painful.
Not for this class. You guys have the easy calculus.
Okay.
Okay.
Good.
Now,
I think all the language and all that is just kind of a lot to take in.
yeah, it is. It is. I mean, it's new language to you guys. I wouldn't bury yourself in that, though. I would just worry more about the processes that you're going over. Okay. Number 2, the limit as x approaches 1 of 5x plus 4. Well, good news, guys. What number can we plug in?
1.
That's it. You plug in 1, you get the square root of 5 plus 4, which gives you the square root of 9, and our limit value is just
3.
3. My goodness. Good stuff, right?
Yeah. Will we be able to use our notes for any kind of exams?
Yeah. Since we're remote, I let you use your notes. I let you use your homework. I let you use the calculators. So
Awesome.
yeah.
So when we're writing this problem out, we got to make sure we write that X arrow sign, showing that.
Yeah. So you want to be proper on your limit notation. So however I'm writing it right now is how you should definitely write it.
And what do you call that?
That is just the limit notation.
Notation. Okay.
Yeah. Okay. We keep going. All right. Number 3. Find the limit as x approaches 4 of x minus 2 over x. Guys, you can't make it any easier. What number are we going to plug in for x?
4.
4. So I'll just rewrite it again. X approaches 4 of x minus 2 over x. This becomes 4 minus 2 over 4. We'll get 2 over 4, and our limit is 1/2. Everybody good with that?
Hang on, sorry.
Go ahead.
Just trying to copy this down so I can see. So technically every time like the X, it just tells you already like what to plug in basically, right?
That's it. It's just saying, hey, plug in 4 or plug in whatever number and see if it works.
Okay. And if it doesn't?
If it doesn't, let me see. Do I have an example of where it doesn't? I sure do. Number 4. If it doesn't work, we have to go back and fix it algebraically. So let's check that out. Everybody good with this one?
Yeah.
All right.
Yes.
All right. Number 4. So going off that same process that we learned, we said, hey, just plug in the number. Well, let's see what happens this time when we do so. So I'll rewrite it. And now I'm going to plug in 2. And you'll get 4 minus 4 over 2 minus 2, which gives you 0 over 0. Now, does anybody know what 0 over 0 is?
Undefined.
That is undefined. It's undefined.
Careful. So 1 over 0 is undefined.
Then it
0,
doesn't exist, right?
0 over 0 is
1.
called
Is it not?
indeterminate.
Oh,
Oh.
Oh,
what about
right.
that word?
Indeterminate is whenever you get a 0 over 0 answer, right? So this means that, hey, plugging in the number from the beginning didn't work out for us. So we have to go back to the beginning of the limit and figure out another way to solve this. So I'm going to rewrite it again. And I want you to think algebraically. How could we algebraically simplify this before plugging in that number again?
The x, the second power, maybe we could.
Did you combine the 2 and the 4?
Can't combine anything. So remember, we can't cancel anything or any of a sort like that because these terms are connected by subtraction. So there's nothing we can do by that way. So when I say think algebraically, I mean, your brains are going, how about factor? X squared minus 4 is a difference of what?
Squares.
Squares. And
It'd be
can
2
you
plus 2.
factor a difference of squares?
Yes.
Yes, you can.
What does it factor to?
It's x plus 2 and x minus, x minus 2.
X plus 2, x minus 2 over x minus 2. And now what is going to happen?
Cancel.
It's gonna work.
Cancel.
It cancels the x minus 2.
And you're left with the limit as x approaches 2 of x plus 2. And now, if I plug in 2, what is my limit going to be?
4.
4. Now, 4 is very different from what you got in the beginning, right?
Definitely. Do you
Pretty
mind
cool.
zooming out? So I can
Yeah,
take
yeah,
a
yeah.
picture
I got
for
it.
that. I was
There you
gonna
go.
say, 'cause for a second, I was going to leave it at the x plus 2, but that wouldn't be solved. So that's
Nope. So you have to
wanna
plug in
remember
that
that.
2.
exactly. All right, thank you.
Any questions on that? So if you end up getting 0 over 0, then it's going to be indeterminate. And you have to go back at it and look at it in an algebraic way. Can I factor it? Can I cancel something? What can I do to fix this? If you do end up in a situation where you get undefined, such as 1 over 0, then you can go back and look and fix it. But if it doesn't fix, then this limit would not exist.
So it'd be indeterminate.
Well, 1 over 0 is undefined and does not exist. Indeterminate's indeterminate. So 0 over 0, infinity over infinity are the only indeterminate forms. 1 over 0, or any number over 0, is called, this is
Undefined.
called undefined, which if you're messing with limits, will lead to does not exist. But indeterminate can always be fixed. Always. Okay. Last one on here. Number 5. The limit as x approaches 3 of x squared minus x minus 6 over x plus 2. Well, let's do what we've been doing. Let's go ahead and just plug in that 3. And see if it works out. Nine minus 3 minus 6 over 5. Which 9 minus 3 is 6. 6 minus 6 is 0 over 5. And what is 0 over 5?
Indeterminate.
Careful. 1 over 0 is undefined. 0 over 0 is indeterminate. Zero over any money, any number is
0.
0. Don't confuse yourself.
So whenever it's 0, we can just leave it like that, or we don't have to remix that one?
Nope, don't have to fix it. 0 is a good answer as long as
All
it's 0 over a number.
Okay, perfect. Thank you.
Right? Yeah. So some notes, right? Some notes. 0 over any number is 0. Any number over 0 is undefined, but in terms of limits, it will be does not exist. And then 0 over 0 is indeterminate. So just some notes for you to have. Okay. Any questions before moving on? Okay. All right. Last page. Okay. So what we're given here is called a piecewise function. I know you saw these in 1324. So these are called piecewise functions. I'll write it down. So on this one, we will learn how to connect limits with the restrictions on piecewise functions. So a piecewise function is a function made of multiple functions with multiple restrictions. So this is called a piecewise function. Here are the functions, here are the restrictions. So if we follow this restriction, this means we get to use the first function. If we follow this restriction, that means we get to use the second function. So let's learn how to connect limits to piecewise functions. So for number 1, it says, find the limit as x approaches 2 from the left of f of x. So if we are approaching 2 from the left side, let's look at our restrictions. If I approach 2 from the left, does that mean my x values are smaller, are less than, or are they greater than?
Less than.
Less than. Good. Remember, if you ever approach from the left, your x values are always less than. So this means that this limit connects to this restriction, and this restriction connects to this function. So since that limit connects to that restriction, this means we are going to use the function x squared plus 1. And what number are we going to plug in for x?
2.
2. That's it. So this becomes the limit as x approaches 2 from the left of x squared plus 1. And we're going to plug in 2. And 2 squared plus 1 is going to give me 5. Okay. Any questions on that part? So you are connecting limits with restrictions. All right. Next one. Now it says, find the limit as x approaches 2 from the right of f of x. Well, I'll ask you again. If you approach 2 from the right, are your values smaller or greater than?
Smaller. Greater than. Sorry.
Greater than. If you ever approach a number from the right, then your numbers are greater than. So this limit connects to this restriction, which means we are allowed to use this function x minus 1. So I'll rewrite it. The limit as x approaches 2 from the right of x minus 1 means we plug in 2, and the limit from the right side is 1. Any questions on that? Okay. And now the next question is just based on that theory, the definition of a limit. So number 3 says, what is the limit from both sides at 2? So what is my left-hand limit here?
It's 5.
5. What is my right-hand limit?
It's 1.
Are those equal?
No.
Therefore, the limit as x approaches 2, what?
5.
Does not exist.
Does not
yeah.
exist. There you go. Because the left-hand limit at 2 is 5. The right-hand limit at 2 is 1. 5 does not equal 1. Therefore, a limit cannot exist from both sides at 2. That's everything we touched on today. And now my last question has nothing to do with calculus at all. It's again, learning how to read function notation. Number 4 says, find f of 2. So this says, when x is exactly 2, what is the value of y? Now, I ask you, do any of these restrictions allow x to be exactly 2?
Yeah, the first one.
The
The first one. Good, because that inequality says less than or
Equal to.
equal to. So therefore, this function notation connects with this restriction, which means we get to use this function. And we already know, good, we already know the value when you plug in 2. You're going to get what?
5.
5. That's it. There you go. And those are limits, y'all.
That's pretty cool.
The homework is